Okay, good afternoon, all. Today we are going to see a 2-bit synchronous counter, right? It is up counter. In last lecture, we have gone through all types of ripple counter or asynchronous counter, wherein we check up counters, down counters, up down counters, positive age triggered counters, negative age triggered counters, all types of ripple counters that we have gone through yesterday in last lecture, right? So today we are going to see about synchronous counter. So let me share my screen first. Is my screen visible? Is my screen visible? Okay. So there are few steps that we need to follow to design a synchronous counter, right? So we start with first 2-bit synchronous counter. I'll explain you all the process to design a 2-bit synchronous counter. So if you understand the procedure, no, you will also understand how to design 3-bit, 4-bit synchronous counters, wherein that up counter or down counter, it may be up counter or down counter. You can design those by using this procedure. So there are certain steps available. Steps are there on your screen. So for 2-bit synchronous counter, total 5 steps you need to keep in your mind. So first is you need to decide on number of flip-flops. How many number of flip-flops we are required to design a circuit. Then excitation table of flip-flop that you are going to use. So which type of flip-flop you are going to use, you must know the excitation table of that flip-flop. Then you need to draw a state diagram for that flip-flop, and based on state diagram and excitation table, you are going to draw a circuit excitation table, or you can say a specific excitation table for this circuit, right? That is your next step. And based on that excitation table, you are going to obtain a simplified equation using KMAP for given counter or given circuit, right? So based on a circuit excitation table, you are going to find out inputs, and rather you are going to find out simplified equation for that circuit. And what is you are using for that? You are using KMAP for that, right? And after simplified equations with you are going to draw a circuit diagram or logic diagram for 2-bit synchronous counter. So let's start with first step. What is my first step? Okay, what is my first step? Hmm? First step का है? Need to decide a number of flip-flop. So since uh, my flip-flop is 2-bit, right? We are going to have a 2-bit synchronous counter, right? That means how many flip-flops are required? 2 flip-flops are required, right? 2 flip-flops are required. Since we are going to design a counter, right? We are going to design a counter. Which flip-flop is basically required is T, sorry, T flip-flop is basically we require. T flip-flop is internally JK flip-flop with logic 1, right? So it is in toggling. So we are going to use a JK flip-flop for this counter, right? So it is a 2-bit synchronous counter. So 2 flip-flops are required. Since it is counter, T type of flip-flop we are going to use. Internally, this T flip-flop is JK flip-flop, which is connected to logic 1, right? So it is a JK flip-flop. So we must understand, we must know the excitation table, right? So excitation table for JK flip-flop, right? So excitation table, what is excitation table? Hmm? Yes, tell me what is excitation table? From present state and next state of output, we are going to identify what all inputs we require for flip-flop is basically there in excitation table, right? So my present state is there, then next state is also there. Present state is referred as Qn, whereas next state is referred as Qn plus 1. And based on that, we need to identify inputs G and K. So we know the excitation table. We have gone through how actually we draw excitation table for flip-flops, right? So excitation table with us, right? So this is basically my excitation table for JK flip-flop, right? So this is basically excitation table. This is my second state. So we are using JK flip-flop. So we are having excitation table with us on screen. Now next stage is we need to draw a state diagram, right? So next step is need to draw a state diagram. So how many states we are there in a counter is actually based on this formula, right? Whereas n is number of flip-flop, right? So on this formula, we are actually finding a state. So how many flip-flops are there? Two flip-flops. So total four states are there for this counter, right? So four states are required for this counter. So how many states are there? Four. That is 0, 1, 2, 3, right? So those are four states. So based on this, we need to draw we need to draw state transition, right? We need to oh sorry, we need to draw a state transition diagram. So how many states are there? Four states are there. If we suppose those states are S0, S1, S2, S3, then we need to write those states. See, this is my S0, S1 state, S2 state, S3 state, right? So since it is 2-bit counter, we have four states, right? So four states and combination in case of bits are 0, 0, 0, 1, 1, 0, and 1, 1, right? So S0 is 0, 0, S1 is 0, 1, S2 is 1, 0, and S3 is 1, 1. So those are my states, right? Which is basically output. This is my Q2 and this is my Q1, right? So this is basically, states of output of flip-flop, right? So Q1's output and Q2 output are basically there, right? Now, what we need to draw in next step is we need to find whether my counter is up counter or down counter, which need to show there in state diagram. There are total four states: S0, S1, S2, S3, and since my counter is up counter, it is incremental and upward direction, right? So this is my first transition. Then from S2 to S3 is my next transition. S2 to S3, sorry, S1 to S2 is second transition, S2 to S3 is third transition, and again from S3 to S0 as a initial transition, right? So this is basically called a state transition diagram for given counter, right? Are you with me? Are you with me? समजलंय का इथपर्यंत काय केलं आपण? Yes, yes. Okay, thanks for your reply. Right. So this is how we draw a state transition diagram, right? Now next is we need to draw a excitation table, right? We need to draw a excitation table. So in case of, you know, this is my present state, then next state, right? Now this is, a circuit, or you can say circuit excitation table. So we have two inputs, that is basically J1 K1 and J2 K2, right? So those are basically two inputs and two output, that is Q1 Q2, and next is again Q1 Q2, will consider it as Q1 star and Q2 star, right? So my present state of output is, if those outputs are 2-bit, then combination for that, sorry, combination for this 2-bit output is 000110 and 1, right? This is basically a combination for 2-bit. Now what we need to find here is next state of this. So if suppose my first output is 00, my first output is 00, then next state would be 01. So that I need to write here. My present state is 01, then my next state would be 10, right? That I need to write here in next state. If my present state is 10, then my next state would be 11, right? That should be my output or next output. And if my present state is 11, then my next state would be again at initial position, that is 00, right? This is how we can draw a next state for our circuit excitation table, and this is how we can write a output Q1 and Q2 and Q1 and Q2 in next state or star, right? So this is basically called uh, what we say outputs for circuit excitation. Now what we need to identify is, we need to write, inputs, right? So we are trying first for J and J1 K1, and then we'll try for J2 K2. So in this case, my input or present output is 0 and my next output is 0. In that case, what would be the input in JK's excitation is this 0 and don't care. Now my input on present output is 0 and my next output is 1, right? So what is there in circuit excitation is 1, don't care, right? Now next is my input is sorry, present output is 1 and next output would be 1. In that case, what is my inputs? Inputs are x 0, right? Now my next output would be current output would be 1 and next output would be 0. Then what is there in circuit excitation? Don't care, 1, right? This is basically how we need to write inputs for circuit excitation. Now I'll give you a problem statement, you need to identify a next thing. That is, you need to write this table, right? J2, K2, right? Based on Q2 and Q star 2, right? So based on present state and next state of Q2, you need to identify inputs for J2 and K2. Now tell me what would be my first input, right? If my present output is 0 and next output be 1. Yes, tell me, anyone. अरे बोला फटाफट काय असेल नेक्स्ट आउटपुट sorry next input 1 and yes 1 and don't care so 1 and don't care now next case for 1 0 for 1 0 for 1 0 don't care 1 right for 0 1 for 0 1 1 don't care right again for 1 0 for 1 0 yes don't care 1 so this is how we write a excitation table for circuit right this is a excitation table for circuit right now when excitation table is with us now next step would be we are going to find out inputs right we are trying for inputs now this is my J1 this is my K1 J2 and K2 I need to write this is therefore if my J1 is like this right so 0 1 don't care now for J2 for J2 oh sorry this is K1 sorry J2 this is K1 J1 and K1 for K1 don't care 0 1 right those are basically Q Q1 and Q2 Q1 and Q2 0 1 0 1 0 1 0 1 so those are basically Q1 and Q2 now for J2 for J2 1 don't care 1 don't care and for K2 don't care 1 don't care so this is Q2 Q1 Q2 Q1 let's suppose few values here now what is the next step here is we need to reduce the thing right so where actually one lies no we need to write a or find out a group there right so in this case one is there so we can group like this right So J1 basically is, this is what Q1 is converted from 0 to 1. So Q1 cancelled. Q2, Q2 with 1 is Q2, right? And not complement, right? So this is basically 1. So this is Q2. Then we'll try for K1. K1 also we can have group like this, right? So Q1 is cancelled, Q2 holds, Q2's value is, Q2's value is 1. So K1 basically is again Q2, right? Now, this is also 0, 1, 0, 1. We group 1, 1 here. Q1 is cancelled there. Mm, we have don't care over there, right? So we can also use all don't cares, right? It becomes what? It becomes, J2 becomes Q2 complement, right? But why to use again Q2 complement there? We can have group like this as well. डोंट केअर आहेत सो कॉड सुद्धा करू शकतो. जर कॉड केलं तर काय होईल, हे सगळेच कॅन्सल होतील. म्हणजे Q1 पण कॅन्सल होईल आणि Q2 पण कॅन्सल होईल, राईट? या केसमध्ये काय कन्सिडर करायचं? 1 कन्सिडर करायचं, राईट? इट इज बेसिकली ट्रू, राईट? So J2 is 1. And for this as well, we'll have a chord, right? आपण directly असा group करू शकतो. So K2 also becomes 1 there. Otherwise हे Q complement आणि हे Q होणार जर आपण group केला तर. But that variables also we can remove. So basically we convert it to chord and this is also becomes a chord. If it is chord, it is 1, right? We can have 1. We consider it is 2, right? So this is basically 1. So next date is, now we have, sorry, we have we have 4 inputs now with us. So we can draw now a circuit, right? So what is my what is there in my counter is, we require 2 counters. We have inputs like J1, K1, Q1, Q complement 1. This is basically J2, K2, Q2, and Q2 complement. So this is flip-flop 1, and this is my flip-flop 2, right? Now, where actually my J1 and K1 is, now J1 and K1 are basically Q2, right? So we connect Q2 to J1 and K1, right? Now what is my J2 and K2? J2 and K2 directly are 1. So we can connect this J2 and K2 to logic 1, right? Since this is a synchronous counter, we can have a clock signal same for both the flip-flop. This is my clock signal. Now, where is output, right? So this is output Q1 and this is output Q2. This is how you need to write you need to draw a 2-bit synchronous counter based on all those steps, right? So J1 and K1 are connected to Q2 since it is there in expressions, and J2 and K2 are connected to logic 1, right? Clock signal is directly applied to all the flip-flops which are present there in circuit that need to directly pass to this, right? So this is how we are designing a 2-bit synchronous counter. हे clear झालं का? Is it clear to all? Is it clear to all? याच्यात काही प्रॉब्लेम आहे का तुम्हाला सिंक्रोनस काउंटर मध्ये? ओके, सो याच्यात फक्त काय ऍड होईल? 3-बिट 4-बिट, राईट? आणि अप डाऊन काउंटरचं मगाशी मी सांगितलं तसं स्टेट ट्रान्झिशनच्या केसमध्ये ते चेंज होईल, राईट? स्टेट ट्रान्झिशन जर अप काउंटरला अपवर्ड डिरेक्शनला असेल तर डाऊन काउंटरला ते डाऊनवर्ड डिरेक्शनला. सो त्याच्या स्टेट सर्किट एक्साइटेशन टेबल मध्ये चेंज होणार, राईट? सो यू नीड टू राईट दिस इज ऑल्सो देअर इन सर्किट एक्साइटेशन टेबल, कारण त्याचं जे रादर स्टेट ट्रान्झिशन आहे फ्रॉम स्टेट 1 टू स्टेट 2, राईट? ते अपवर्डला रादर अपला अपवर्ड डिरेक्शनला राहील आणि डाऊन काउंटरला डाऊनवर्ड डिरेक्शनला. सो त्या व्हॅल्यूज चेंज होतील. इफ दोज व्हॅल्यूज आर चेंज देन इनपुट्स आर ऑल्सो चेंज, राईट? सो त्या केसमध्ये त्याचे इनपुट सुद्धा चेंज होतील, right? So this is how you can design a 2-bit synchronous counter. So you also may have 3-bit synchronous counter. You can also use up-down counter in this case as well, right? So you need to design a 3-bit synchronous down counter, right? Your homework is 3-bit synchronous down counter, right? By using those all steps, right? This is your homework. You need to design this circuit. ओके, याच्यात कुणाला काही इश्यू आहे का? याच्यात काही कळलं नाही वगैरे असं आहे का? I'll quickly revise all those things which are there again. Okay, so those are steps available, right? What all steps? We need to decide flip-flop, then need to draw excitation table, state transition diagram, need to draw circuit excitation table, then simplified equation based on circuit excitation table, and we need to reduce that equation by using KMF, right? And then we need to draw a state transition, right? Since it is 2-bit, we require 2 flip-flop, right? And it is counter, then we are going to use T flip-flop, right? So T flip-flop are internally JK flip-flop with logic 1, right? So we know the excitation table which is there about a JK flip-flop, right? So excitation table is there. Then we need to find us how many states we require. Based on those states, we are going to draw a state transition diagram. And based on state transition diagram, we find out a circuit excitation table. So circuit excitation table, we use also excitation table of JK flip-flop. And based on that excitation table, we are actually putting few values there for this circuit, right? And then next step is we reduce that equations or inputs by using EMF, right? So we found inputs there, what inputs we require for first flip-flop, what inputs we require for second flip-flop, right? We identified that by using EMF, and then we draw a circuit by using those inputs which are come out from EMF, right? This is basically a 2-bit synchronous flip-flop. Sorry, counter. Okay, till now it is clear to all. Is it clear to all? Okay, so should we move to next topic? Okay, so next point is ring counter and twisted ring counter. Twisted ring counter, right? Which is basically called a Johnson counter, right? Twisted ring counter is also called a Johnson counter. So ring counter is an application of shift register, right? A shift register's application, right? So ring counter is basically a application of shift register, right? So how ring counter works? The ring counter is, we'll try for 4 bits. Okay, we'll try for 4 bits. So those are my 4 flip-flops, right? So in register, this is basically my arrangement, right? If I consider this is A, B, C, D, then this is my data input D, A, Q, A, D, B, Q, B, D, C, Q, C, D, D, okay, and Q, right? So in case of ring counter, we apply, or in case of shift register, we apply clock pulse to all the clock input, right? So ring counter is a special type of arrangement wherein output of last flip-flop is connected again as input to first flip-flop, right? And how to set this flip-flop is, this flip-flop is set by using ORI, overridden inputs. Now, those overridden inputs are connected as, those are my clear input, active low, and for first flip-flop, it is connected to preset, right? It is connected to preset. So why it is called overridden input? Because for all 4 flip-flops, first flip-flop is become preset by this input over input, and all other becomes clear. That means the output after ORI for this is 1, 0, 0, 0, right? If we pass overridden input to this, right? And after that, if you apply next clock pulse to it, this 1 is there as the output and passed as data input, right? So initially, the case is like 1, 0, 0, right? Initially, and then when you apply first clock pulse, then this 1 is passed to here, it becomes 0, all other 0. And second clock pulse, the output is 1 here, so it is passed as data input, and it is passed here, this 1 becomes 0, right? So 0, 1, sorry, 0, 0, 1, 0. Again, this 1 is passed as input to this 0 becomes 1, this 1 becomes 0 for third clock pulse, right? Again, this is 1, so this is passed as 1, clock signal is applied, this is toggled, and this 1 is applied again as data input here, and this 0 becomes 1, right? So at 4th clock pulse, it is 0, 0, 0, right? So this 1 basically is moving from one flip-flop to another, and again from last to first, right? This is why this flip-flop, this counter is called a ring count. कळलं का इथपर्यंत? त्याला रिंग काउंटर का म्हणतात कळलं का? ओके ओके, याच्यात कुणाला काही प्रॉब्लेम नाही ना? कोणीतरी रिपीट टाकलं होतं, कोण आहे ते? Who's that? ज्याचा रिप्लाय रिपीट होता कोण होता? म्यूट करा, काय प्रॉब्लेम आहे?
सर कसं काढलं?
हा,
रिंग काउंटरचे 1100 ते व्हॅल्यू कसं काढायचं?
तेच का रिपीट करायचं? तुम्हाला कुठेपर्यंत कळलंय सांगा? का तुमचं लक्ष नाही म्हणून रिपीट करायचं?
नाही, व्हॅल्यू कसं काढायचं ते कळलं नाही.
ओके, सो ओव्हररिडन इनपुट हे जे पास केलं ना, ओव्हररिडन इनपुटनी इथं प्रिसेट आहे. प्रिसेट म्हणजे काय होतं? प्रिसेट म्हणजे काय होतं? पल्लवी अनम्यूट करा स्वतःला. प्रिसेट म्हणजे काय? अरे प्रिसेट म्हणजे काय होतं?
तिथे व्हॅल्यू 0 असते.
हा, व्हॅल्यू 0 असते. क्लिअरला 0 होते. फ्लिप फ्लॉप प्रिसेट करतो म्हणजे आपण सेट करतो, राईट? 1. आणि फ्लिप फ्लॉप क्लिअर करतो म्हणजे आपण रिसेट करतो 0, राईट? सो या केस मध्ये क्लिअर होतो. दॅट मीन्स फ्लिप फ्लॉप विल होल्ड दी 0 देअर, आणि फ्लिप फ्लॉप या फर्स्ट फ्लिप फ्लॉप आहे तो आपण प्रिसेट करतो. दॅट मीन्स हा 1 होईल, राईट? सो इनिशियली 1 0 0 0 असं राहील, राईट? when we apply next clock pulse म्हणजे काय होणार? आता हे सगळे टॉगल फ्लिप फ्लॉप आहेत. टॉगल म्हणजे काय होणार? 0चं 1 1चं 0, राईट? आता या केस मध्ये इथं 1 आहे म्हणजे याचं डेटा इनपुट 1 होणार, आणि क्लॉक पल्स अप्लाय झाले की हा 1चा 0. इथं डेटा इनपुट 1 आलंय म्हणजे हे टॉगल होणार, 0चं 1 होणार, राईट? ऑब्विसली नेक्स्ट क्लॉक पल्सला काय होणार? 0 1 0 0. अगेन हा 0 इकडं पास झाला, राईट? हा 0चा 1 झाला म्हणजे 0 0 1 0, राईट? हा 1 झाला. आता परत क्लॉक पल्स, नेक्स्ट क्लॉक पल्सला काय होईल? हे आहे असे 0 राहतील, जिथं परत टॉगल काय होणार? हा टॉगल डायरेक्टली 1 आहे तो पास होणार 1चा 0, राईट? सो या केसमध्ये याला इनपुट आलं, तो हा टॉगल झाला, राईट? आता इथं 1 आहे, हा 1 याला पास झाला म्हणजे इकडं परत हा 1 आला, डेटा इनपुट 1 आलं, क्लॉक पल्स अप्लाय झाली, परत हा 0चा 1 झाला म्हणजे फोर्थ क्लॉक पल्सला हा असा आला. दॅट इज बेसिकली हे रिंग. म्हणजे 1 जो आहे तो इथून स्टार्ट होतो, तो या फ्लिप फ्लॉप मधून मूव्ह होऊन परत होता तसा पहिल्या फ्लिप फ्लॉप मध्ये. दिस इज व्हॉट अ रिंग काउंटर इज. कळलं का? काय कळलं? काय कळलं? पल्लवी काय कळलं?
पहिल्यांदा प्रिसेट होतं तेव्हा पहिल्या ब्लॉक मध्ये 1 येणार.
ब्लॉक नाही, तो फ्लिप फ्लॉप आहे. फ्लिप फ्लॉप आहे.
फ्लिप फ्लॉप मध्ये आणि बाकीचे ते 0-0 असणार क्लिअर मध्ये. नंतर मग पुढे गेल्यानंतर दुसऱ्या फ्लिप फ्लॉप मध्ये 1 येणार आणि बाकीच्या 0-0 होणार.
Right. Very good. So this is about, a ring counter. Now next is twisted ring counter. तो ट्विस्टेड रिंग काउंटर मध्ये चेंज काय आहे, हे जे क्यू कनेक्ट करतात त्याच्याऐवजी Q1 कनेक्ट करतात, राईट. Q1 कनेक्ट करतात फर्स्ट डेटा इनपुटला आणि ओव्हर रिडन इनपुट मध्ये जे फर्स्ट साठी आपण प्रिसेटला क्लिअर कनेक्ट करत होतो ते सगळेच क्लिअरला कनेक्ट करतात, राईट, इन केस ऑफ ट्विस्टेड रिंग काउंटर, राईट. सो दिस इज हाऊ ट्विस्टेड रिंग काउंटर लुक्स लाईक, राईट. आता या केस मध्ये फक्त काय होतंय की हा सगळेच इनिशियली झिरोला असतात, राईट. सगळेच इनिशियली झिरोला असतात. बट वेन यू अप्लाय क्लॉक पल्स, हे जर झिरो असेल तर क्यू कॉम्प्लिमेंट 1 असतं, राईट. सो हे 1 इथं अप्लाय होतं आणि हे 1 डेटा इनपुट इथं येतं, राईट. सो फर्स्ट क्लॉक पल्सला हे 1 0 0 0 असं होतं, राईट. सो नेक्स्ट क्लॉक पल्स अप्लाय केला की तुम्ही काय होतं, हा 1 असतो, तो 1 इथं ऍज इट इज राहतो, राईट. आणि हा 1 डेटा इनपुट इकडं, हा 1 इथं, म्हणजे हा परत 0चा 1 होतो, राईट. म्हणजे 1 1 0 0. सिन्स आता हा 1च का राहणार, तर इथं डेटा इनपुट ऑलवेज 0 आहे आणि याचा कॉम्प्लिमेंट 1 आहे, राईट. दॅट इज वाय हा 1 कंटिन्युअसली अप्लाय होत राहतो या फ्लिप फ्लॉपला, राईट. त्यामुळे हा 1च राहतो आणि हे पास होत राहतात 1, राईट. सो हा नेक्स्ट स्टेजला काय होतं, परत हा 1 होतो कंटिन्युअसली, 1 1 1 0, राईट. परत काय होतं, 1 1 1 1 असं होतं. आता या केसमध्ये ज्यावेळेस फोर्थ फ्लिप फ्लॉप इथं 1 येतं त्यावेळेस क्यू 0 होतो, म्हणजे हा डेटा इनपुट पास काय झाला 0, म्हणजे इथं काय आलं 0, राईट. मग हे 0 होतं, बाकीचे ऍज इट इज 1 राहिलेले असतात, राईट. जे नेक्स्ट इटरेशनला 0, सॉरी, नेक्स्ट क्लॉक पल्सच्या इटरेशनला परत 0 0 1 1 0 0 0 1 and again it will come to 0 0 0, right. This is basically a twisted ring counter, right. इतका चेंज होतो रिंग काउंटर आणि ट्विस्टेड रिंग काउंटर मध्ये. फर्स्ट ऍज इट इज ओव्हररिडन इनपुट असतं ते आपण क्लिअरलाच कनेक्ट करतो आणि जे रिंग काउंटर मध्ये फीडबॅक घेतो आपण लूप मध्ये टाकतो फर्स्ट क्यू टू डेटा इनपुट, तेच ट्विस्टेड रिंग काउंटरला Q1 टाकतो. So this is how twisted ring counter works. This twisted ring counter is also called as Johnson counter. Thank you for